Okay, so as you can see, the quiz just ended, and it ended after precisely 1 hour. I'm going to try writing in blue tonight in hopes that it will erase a little bit better. And this is, of course, going to be just 1 hour to lecture 5 because we used the first hour on the quiz. I have to get through the so-called sampling paradox in order to cover everything that's on the homework. I should say, my wife and I had a very, very busy few days. She was getting out the December issue of the journal she edited, so she had 96 pages to get ready. And by the time I was done with the quiz, the homeworks, and the next batch of outlines, I had 52 pages of math rolling off my printer. Those of you who are here should already have picked up the hard copies of the next batch of outlines and assignments. And I have, for once, I believe, remembered to put everything online right away so that distance learners can download these and print them. Okay, I'm now going to start with topic 12 on outline 4. And this is called Conditional Craps. This is the quickest analysis I know of the probability of making a point in craps. It always seems to me a little too cut and dried, but I think it's rigorous. So here's the idea. You're watching a craps game, and there's such a crowd around the table at the casino that you can't really see the die, so you can only ask people in front of you. And the shooter rolls the die for 7, come 11. And you say, what happened? What happened? Well, he rolled a 4. Okay, so now you know the point is a 4. And shooter cranks up, rolls the dice, blank, blank, blank. The game over? No, it's not over. No, it's not over. Well, it's over this time. Now, the only reason the game will be over is either that event 4 occurs, which is the shooter rolls a 4 and wins. And we know the probability of that event is 3 over 36, or a 12th, because there are 3 ways of rolling a total of 4 on 3 dice. Or S7, which is that the shooter rolls a 7, in which case he loses, and the probability of that is the number of ways of rolling a 7 over the number of outcomes, or 1/6. So, when the person in front of you says, yes, the game is over, you can reason as follows. You can say, I want to know the conditional probability that the shooter won, because I bet on him, given that the game ended, and the event that the game ended is S4 union with S7. So far, so good? Now, what is this? Well, we can blindly use the definition of conditional probability, the probability of S4 intersect the union of S4 with S7 over the probability of S4 union S7. A 4 and a 7 are, of course, disjoint events. Here we have 1/12 plus 1/6. And this looks complicated, but it's really as stupid as can be. If you have S4, intersecting it with the union of S4 and S7 doesn't make a bit of difference. This is just the probability of S4. So we now have 1/12 over 3/12, or 1/3, which is the same answer you get in every other way. And with that quickly done, I want to go on to number 13, independence of 3 events. This is now, I think, one of the most famous counterexamples in mathematics. And amazingly, it was apparently only discovered quite far into the 20th century. This is much, 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 much more elementary than much of the mathematics that was developed in the 19th century and even in the 18th century. But that just indicates that probability theory was a very late-blooming branch of mathematics. And here's what I'm going to demonstrate. I'm going to show that you can have three events, any two of which are independent of one another, but which are nonetheless not independent events. My original example of this was a rather lame one where you had a computer program that with probability 1/4 produced each of the strings A, B, C, and ABC. The current version is due to a former student of mine named Mark Paris, now a senior at Harvard, who out of the blue came up with this wonderful example in a course where I had students present all these topics, and we were doing a bit of probability. Mark, it turns out, is a Yankees fan, but this is such a good example that I'm going to forgive him for it, and I'm going to use his original storyline. So, the storyline is this. George Steinbrenner has decided he needs to strengthen his pitching staff for the upcoming season, and he goes out and secretly negotiates deals with three big-time pitchers. And in the original version, the three big-time pitchers were Roger Clemens, Randy Johnson, and Barry Zito. Of course, now that Randy Johnson is a Yankee, this is moot, but I decided not to change the storyline. And he goes to the commissioner, and the commissioner says, you know, George, even for you, this is a bit much. I need to think about it. And then he pauses and says, I'll tell you what I'll do. Tomorrow morning, I will roll a tetrahedral die. I'm a big Dungeons and Dragons fan, so I just happen to have a tetrahedral die. And here's the deal. If I roll a 1, you get Clemens only, but you can't sign the other two guys. If I roll a 2, you get Randy Johnson only. If I roll a 3, you get Barry Zito only. And if I roll a 4, you hit the jackpot. You get to sign all 3 of these folks. And furthermore, just because I want the nation to be talking about Major League Baseball, I'm going to announce tonight that I'm going to roll this die in the morning, so they'll have some time to think about it. So the word gets out in Boston. The Yanks are going to have a new big-name pitcher, or maybe more than one big-name pitcher tomorrow. And now we can define some events. Event C is the Yanks get Clemens. And what's the probability of that event? Not 1/4. 1/2, because they get Clemens on either a 1 or a 4. Similarly, J says they get Johnson, and the probability of that event is 1/2. And Z is the event that they get Zito, and the probability of that event is also 1/2. And now we can work out some probabilities of intersections. What's the probability that they get both Clemens and Johnson? 1/4, right? Because if the commissioner rolls a 4, they get both of them. And that's also true for getting Clemens and Zito, or for getting Johnson and Zito. So the first question to ask and answer is this. Are the events C and J independent? Opinions? Yes. Why, Dana?
The 1 multiply P of C times P of J, 1/2 times 1/2, and that's a 4th.
Yep. So P of C times P of J,
equals P
which
of
is
C
equal to
intersect.
1/4, is P of C intersect J. So these two events satisfy the definition of independence. And just to convince you that they also satisfy our intuitive notion of independence, you can think, as you go to bed, I wonder whether Roger Clemens is going to be a Yankee tomorrow. The fact that there's a probability of 1/2 for that is going to give me a bad night's sleep, but you sleep nonetheless. Your spouse wakes you up and says, hey, I just heard it on the news. The Yanks signed Randy Johnson. And you think about it and say, well, the probability they've signed Clemens is still 1/2. The news they signed Randy Johnson doesn't tell me anything. That's the way most people like to think about independence. Okay. Now, here's the funny thing, because you can see any pair of these events is independent. And it's tempting to think there might be some theorem that says if events are independent in pairs, they're totally independent, but that's not so. Let's try one more. C, J, and Z independent. Opinions on that? Yeah, Jerry?
Well, I mean, the product of the three is 1/8.
1/8. So Jerry has said correctly that P of C times P of J times P of Z is 1/8, but P of C intersect J intersect Z is what?
1/4.
A fourth. So these are not independent events. Now I can put this in intuitive terms also. You fall back asleep and your spouse comes and says, I just turned on ESPN and the Yanks got Zito too. Now you know the whole story. You say, if they got both Johnson and Zito, now the conditional probability that they've got Clemens is 1. So that means that the probability of the event Clemens conditioned on the intersection of Johnson and Zito is 1, which is not equal to the probability of getting Clemens conditioned on nothing. So these three events, no matter how you want to look at it, are not independent of one another, even though they're independent in pairs. We will not have many occasions to consider large sets of possibly independent events like this, but it's worth knowing that you have to check that for any subset of the events you have, the probability of the intersection of all those events is equal to the product of their individual probabilities. It's not good enough to do it in pairs. For some reason, when I use markers in my freshman seminar on a whiteboard, the whiteboard seems to erase much more cleanly, but maybe I can switch to black and gain a little extra mileage. I now want to move on to compound experiments. And this enlightening observation is one that I extracted from one of the best introductions to probability ever written, which is, of all places, Chapter 2 of Tom Apostle's 2-volume book on single variable and multivariable calculus, where after doing multivariable integral calculus, Apostle goes back, has one chapter devoted to discrete probability, what we're doing to introduce the subject, and then a follow-up chapter where he talks about continuous probability and shows how the multivariable calculus that he has presented can be applied to this topic. And in another course that I teach in the college, I use just the discrete probability chapter from this book, which has nothing whatever to do with calculus, but is, in my opinion, the best single chapter on probability that I have ever seen. Since the book costs $120, I would not advise you to go out and buy it just to get this one wonderful chapter. But here's an interesting insight from it. A standard way of creating independent events that makes people happy with their independence is you do a compound experiment. And a very simple sort of compound experiment is a die roll followed by a coin flip. And on hearing this, you, of course, think, yeah, of course, and the coin flip will be independent of the die roll, because how is the die roll going to influence the coin flip unless you have something crazy like the coin is sitting on a metal surface, and if you roll a 5 or 6 on the die, it creates a short circuit, and the metal surface starts to melt, and it biases the coin, so it has 6/10 of a chance, 6/10 chance of coming up heads. So that's the intuitive idea of independence of events, and that doesn't work with our definition. Because when we say two events are independent, P of A intersect B is P of A times P of B. Where do the events A and B have to live? In the same event space. Okay? This only makes sense if A and B are in the same event space. Now, if you have a coin flip independent of anything else, that's in an event space with 2 outcomes, heads and tails. If you have a die roll, that's in an event space with 6 outcomes, 1, 2, 3, 4, 5, and 6. Those aren't the same event spaces at all. So what we have to do is redefine the events A and B so that they're in the same event space. And here's a nice way to do it. The die roll can come out 1, 2, 3, 4, 5, 6. And then the coin flip will come up either heads or tails. Now, what I'm going to say is completely valid if the die is not a fair die and the coin is not a fair coin. Nonetheless, I will put in, for illustrative purposes, the probabilities that would occur if it's an unloaded die and a fair coin. In that case, each of the individual outcomes for the combination of the die roll and the coin flip has a probability of 1/12. All that really matters, however, is that the entry in every box is the product of the entry for the row and the entry for the column. Now, let's pick some events. Event A is, well, we'll be sloppy about this first. Die shows a 3. Notice there's no closing quote on this yet. In my diagram, if I want to outline that pair of events, if I want to outline the outcomes corresponding to that event, what do I outline? If I want to draw a box around the outcome. All of row 3, yes, thank you. So I can say the die shows a 3, and the coin is anything. And that's an event in the event space consisting of pairs of outcomes, one for the die, one for the coin. Now you got the idea. Event B, which sloppily would be coin comes up heads, should be characterized how? Die is anything. And the coin comes up heads. Notice neither of these events is an individual outcome in our event space, but both of them are perfectly good events, and the intersection of the two events is A intersect B, which is die equals 3, coin equals heads, and the condition that the probability of that event is the product of the probabilities of A and B. This is all now strictly legitimate because these are all in the same event space. This is tantamount to saying the entry in each box of this table has to be the product of the entry for the row and the entry for the column. You've been doing these 2x2 grids for conditional probability problems, and you've probably already noticed they're rather dull if this condition applies, because then the two events involved are independent, and the conditional probability for any event is the same as its unconditional probability. Moving right along, and in fact finishing this outline, we'll go to number 16, which I believe I called accidental independence. 15? Okay, this is number 15. And the general theme of this one is you cannot, in general, tell whether or not two events are independent from a description of the events. You have to know all the probabilities that are involved. This is contrary to most people's intuition. Most people would say, you describe the events to me, and I'll tell you whether they're independent or not, which means I'll give you my gut reaction on whether one could have influenced the other. That's not the definition. The definition is the probability of the intersection is the product of the probabilities. And this is a funny example because it involves two events that are usually not independent, but for one particular value of a probability, they are accidentally independent. I believe Sturzaker has a soccer match in mind when he talks about this, but since we're on the other side of the Atlantic, I'll think of this as a football match and imagine the following highly artificial scenario. We have a Harvard football fan who is incapable of getting to the stadium, but happens to live on Memorial Drive with a window that permits him to see the top of Harvard Stadium. And he says, I really want to know whether Harvard won the coin toss at the beginning of the Yale game. And I say, well, I'd like to help you, but you know the Harvard Corporation is asserting its proprietary interest in the outcome of this game, and nothing about the game can be revealed outside the stadium until the game is over. He said, well, I'd still like to know as quickly as possible. And I say, well, there's a 10-minute delay on the television feed, but I'll tell you what, there's a flagpole in the stadium and a flag that can be hoisted. Maybe I can use that to help. So we now have the following setup. we have the coin toss, and the two outcomes of the coin toss I'm going to call C, which means Harvard won the coin toss, and C complement, which means Harvard lost it. And these two events have probability P and 1 minus P, respectively. And then we have the match, Sturzaker's term. Either Harvard wins the game or Harvard doesn't win the game. Now, this is where it gets really contrived. I say, I'd love to help you out, but I looked into the mechanism for this flag, and it turns out if Harvard won the coin toss, they put the coin in such a way that the flag can be raised only if Harvard wins the game, too. Whereas if Harvard loses the opening coin toss, then the coin is put upside down, and the scoreboard gets checked, and the flag can be raised only if Harvard loses the game. And my friend says, well, you might tell me something. Raise the flag anyway. So we've got this strange event B. Event B is outcome of toss equals outcome of match, or if you prefer, B is C intersect M union C complement intersect M complement. So that's the deal. I raise the flag only if the outcome of the coin toss and the outcome of the match are the same. And my friend wants to know, will this tell me anything useful about whether Harvard won the coin toss? Question.
In the outline, it says event M is win
yes,
the coin toss.
Thank you. There is a typo,
Okay.
Which I have noted here. Event M is win the match. Thank you very much for pointing that out. I noted it and forgotten it. Okay, so my friend is interested, remember, in whether Harvard won the coin toss, not whether Harvard won the game. And I think it's worth looking at some numbers here. Let us imagine that Harvard has a 50% chance of winning the game, but that a highly crooked coin is used for the opening coin toss in such a way that Harvard has an 80% chance of winning the coin toss. And these are independent events. So here are the four possible outcomes. These two are event B, and those two are event B complement. Before the game starts, my friend knows that Harvard has an 80% chance of winning the coin toss. If the flag goes up, what's the conditional probability that Harvard won the coin toss? 4 out of 5, so it hasn't changed. So in the case where Harvard has a 50% chance of winning the match to start with, the information that event B has occurred is useless. It doesn't change the probability of the event C. If my friend is interested in whether Harvard won the game, 50% chance unconditional probability, the flag goes up. What's now the probability that Harvard won the game? 4 out of 5. So if the flag goes up, it says a whole lot about whether Harvard won the game, but says nothing about whether Harvard won the coin toss. If I were to put in some numbers where Harvard had a high probability of winning the game, but the coin was fair, now, if the flag goes up, it says a whole lot about whether Harvard won the coin toss, but nothing about whether Harvard won the game. So there's something funny about this probability of 50%. That's what's going to come out of the algebraic analysis, but I didn't find that the algebra was particularly enlightening about what's really going on. I think these numbers actually told me a bit more. Yeah, I didn't invent this. I didn't invent this example. I just chose the book. The flag goes up in one of two cases. The flag goes up if Harvard won the coin toss and proceeded to go on and win the game, or if Harvard lost the coin toss and proceeded to go on and lose the game. If Harvard won the coin toss and lost the game, or lost the coin toss and won the game, then the flag doesn't go up. Got the deal? Okay, and what I need to show is that the event Harvard won the coin toss and the event the flag went up, while ordinarily these are not independent events, these events happen to be independent in the special case where Harvard has a 50% probability of winning the game. And the way I figure this out is I say winning the coin toss and winning the game are independent events. That may not be precisely true in football, but it's probably a reasonable approximation. And so I can fill in the usual grid with the probability for all intersections of the coin toss event, the game event, and their complements. So those are the probabilities of the four possible outcomes for the pair, what happens with the coin, what happens with the game, and they sum to 1. Now let's work out the probabilities for the individual events. In terms of P and P prime, what's the probability that the flag goes up? What's the probability that the outcome of the coin toss and the outcome of the game are both the same as far as Harvard is concerned?
Just add
times P prime.
P prime plus...
Add P and P prime, and then add on to that 1 minus P times 1 minus P prime. That's event B. So far, so good? What's the probability of event C? That's easy. P. And these two events are independent if the probability of their intersection, which is also easy because it's P times P prime, right? If the flag goes up and Harvard wins the coin toss, that's this specific outcome. It has probability P prime. And the two events are independent if that's equal to the probability of B times the probability of C, which is equal to P prime plus 1 minus P times 1 minus P prime, all multiplied by P. You can see what I mean when I say the algebra is not particularly enlightening. It gives you the right answer, but it doesn't really let you know what's going on. Okay, let's check that this is true. This is what we need for independence. Well, P cancels from both sides. So, what do I have? I have P prime has to equal P prime plus 1 minus P prime plus P prime. No, 2 minus signs here. I'm okay. So now I have to figure out whether that is ever true. And there's a nifty way to factor this if I can remember it. Ah, yes. I get 2p prime, that takes care of both those terms, minus 2p prime, that takes care of both those terms, equals 1 minus p, or 2p prime times 1 minus p equals 1 minus p. 2p prime equals 1, and p prime equals 1/2. So these two events are independent if and only if p prime is equal to 1/2. The example itself isn't particularly important, but the lesson you should take away from this is every once in a while, two events that look as though they're not independent are accidentally independent because of a particular set of probabilities that's assigned to them. And that means you can almost never say with certainty those two events are not independent events. Okay, that finishes up outline 4. Now we move on to outline 5. And I have to get through at least 2 topics on this so that you can do the homework. And if I have time, I will do Wisdom of Solomon, too, which is by far the most entertaining of the first 3 examples. Everything in this outline is a curious, somewhat advanced topic in conditional probability, and what I'm leading up to is the most famous of all these topics, namely Simpson's paradox, which is discussed in at least hundreds and probably thousands of cases on the web, and is discussed properly about 1% of the time. And on the web you can find all sorts of journal articles published about this, written by people who appear to believe they're the first ever to have noticed this and who don't give a particularly good explanation of it. I am planning to give you next week the best explanation of Simpson's paradox ever given, so you will not only understand this so-called paradox, but under the right circumstances, given 2 products, you will be able to take the inferior product and launch a marketing campaign that will convince 99% of the people in the world that your product is better. So this is how to lie with statistics in spades. But I want to lead up to this with some simpler examples. And the first one is based on what's called sudden death from the book. So we're into outline 5, topic number 1, sudden death. This is a dueling problem like the one on the quiz, but the analysis is in terms of conditional probability, so you can get the right answer without summing a series. Having used up one pair of duelists on the quiz and another on the makeup quiz, I went into American history and realized that Alexander Hamilton and Aaron Burr apparently once fought a duel. And the way we're going to work this out is they fire in the order H for Hamilton, B for Burr, H, B, and so on. They keep shooting alternately until one of them kills the other. A shot either misses completely or it kills the opponent, and Hamilton is a better shot than Burr. The opposite was true historically, was it not?
Burke
Burr killed Hamilton. Well, I'm rewriting history. Hamilton kills Burr with a probability P equals 1/3 on any given shot. And Burr is a lousy shot. Burr kills Hamilton with a probability of only 1/6. Okay, let's consider one round of this duel. So what do we have for one round of the duel? Well, we can think about the probability that Hamilton wins the duel. I think I abbreviated him H in the outline. I abbreviated him A in the outline, but I started with H here, so that's okay. So we can think of it like this. Consider one round of the duel. There are three outcomes for the first round of the duel. Either Hamilton kills Burr, or Burr kills Hamilton, or they both miss and we go on to the next round. And if we go on to the next round, the duel might as well be starting right over. The secret of this sort of analysis is to find one of these situations where, in effect, everything might as well be starting over. So, the probability that Hamilton will win the duel is the probability I'm going to say this in conditional probability terms, but just write the numbers. So, what is the probability that Hamilton wins the duel given that Hamilton kills Burr with his first shot? 1. Okay. So that's the conditional probability. The conditional probability that Hamilton wins the duel given that he kills Burr on his first shot. And what's the probability that he kills Burr on his first shot? 1 out of 3. What's the probability that Hamilton wins the duel if he misses and Burr then proceeds to kill him? 0. And now you have to be a little bit careful with this. What product of two fractions is the probability that Hamilton misses and Burr then hits? 2/3 times 1/6. Now, what is the probability that Hamilton wins the duel if both the duelists miss on their first shot? What's the symbol for that? I mean, you're one of the seconds, and you come saying, there's a probability of such and such that my man will win the duel. Bang, miss. Bang, miss. Do you change your mind about the probability that your guy will win the duel? No, it's still the same. So we've got P of A again, and this time we have to multiply by the probability that both these incompetents miss, which is 2/3 times 5/6. Everyone with me so far? So what we're doing is we're conditioning on the outcome of the first round. We can say in the first round there are three things that might happen, and the textbook refers to these as P, Q, and R generically. Yeah, Jerry?
What is A in this outline?
Oh, A is my mistake from using the first name instead of the last name. When I wrote the outline, I thought, well, events are often called A and B, so I'll use A for Alexander and B for Burr. And then I slipped and I'm using just surnames. My mistake. Yes. The one says, if Hamilton goes, bang, you're dead, he wins the duel. So the conditional probability that he wins the duel, given that he fires a shot that kills Burr, is, of course, 1. Okay? Now we can get an equation. And the generic equation is P of H times 1 minus R, now that I've assigned names to these things, is equal to P. So P of H, the probability that Hamilton wins the duel, is P over 1 minus R, which is 1/3, the probability that he kills him on the first shot, divided by, this simplifies to 10/18, so it's 1 minus 5/9, so that's 3/9 over 4/9, or 3/4. And in the problem on the quiz, if you sum the geometric series, you would have had a geometric series where you said, well, on the first round, there's a 5/9 chance that it's out inconclusive. Then there's 5/9 squared for 2 rounds and 5/9 cubed for 3 rounds and so on. And you coax this 1 over 1 minus 5/9 out of that analysis instead. But this is a much quicker way of getting the answer. And this is the first of many examples you will see where you use the idea of conditional probability to get an equation that you can solve for a probability. That's frequently a much more attractive alternative than summing an infinite series to get the answer. Okay, last example. The so-called sampling paradox. So this is topic 2. I know that extension students like to take courses and then go out and get jobs. Frequently become doctors, lawyers, investment bankers, and so on. But let's just say your goal in life is to become a big-time insurance agent. So you take this course, you get an A in it, you go out to interview with an insurance agency, and the interviewer says, well, is there anything in your academic background that will help you out in the insurance business? To which the right answer is there's a whole lot, because ultimately insurance is one of the great forms of legalized gambling, and an insurance company that isn't pretty good at estimating probabilities and working with them will be out of business in fairly short order. But here is a very, very simple example of how out of a whole bunch of independent events you can create 2 events that are not independent. And here's how it works. I'm going to change the numbers from what are in the book. And we're talking about car accidents. So event A1 is that an insured individual makes a claim in the first year. And event A2 is that this person makes claims in both the first year and the second year. And now I'm going to make the rather unrealistic assumption that someone's driving success in year 2 is independent of their success in year 1, that whether someone has an accident in the second year is independent of whether they have an accident in the first year. But it depends on gender. So I'm going to assume for males, the probability of a claim which I believe Sturzacher calls mu equals 0.3 in any given year, and making a claim is independent from one year to the next. While for females, the corresponding number, which I think Sturzacher calls lambda, is only 0.1. Now, you're sitting in your office. Some guy comes in and says, I'd like to buy an insurance policy from you. And say, fine, we can do business. He said, oh, I've got to tell you, I did have a claim last year. And I say, that doesn't bother me. I've studied the actuarial evidence. That doesn't affect the probability that you'll have a claim next year. Those are independent events. My estimate of the conditional probability that you will make a claim in the next year is 0.3, based on the fact that you appear to be a man. Okay. Your next client comes in. It's a woman. She says, I'd like an insurance policy. I've got to be upfront with you. I submitted a claim last year. I say, no problem. Year-to-year outcomes are independent events. The conditional probability that you'll submit a claim in the forthcoming year is still 0.1, independent of the fact that you submitted a claim last year. So whether it's a man or a woman, claims are independent from year to year. Everyone happy with this so far? Now, one of your buddies calls up and says, hey, would you like to take over one of my clients? You know, we insure just about half men, half women. I've got too many accounts, and I'd just like to pick one of my clients at random and turn it over to you. Say, well, sounds okay. He said, well, I did it. And by the way, I've got to warn you, I looked at this person's record, and they submitted a claim last year. And you say, amazingly, thinking very quickly, sorry, I won't do that. That's a worse risk for me than taking someone who walks in off the street. So that's what I'm going to prove to you. Okay, here goes. We're going to assume half men, half women. And the idea is we pick a person at random, and we want to know the probability that they make a claim in the first year. Now, this has to be conditioned on the case of a man and the case of a woman. Each of those events has a probability of 0.5 if we're picking the insured individual at random. So we have 1/2 times 0.3 plus 1/2 times 0.1, which is 0.2. Everyone comfortable with that? Pick someone at random, 50% chance of the man, 50% chance of the woman, average together the two probabilities, and we get 0.2. Now we'll do the same thing for the event which is claim in the first year followed by a claim in the second year. What is the probability that a male driver will make a claim in each of the first 2 years, according to this model? 0.09, right? Because first year and second year are independent, 0.3 for each, hence 0.09. And half the drivers are women. What's the probability that a woman will make a claim in each of the first 2 years? 0.01. And when I average 0.09 and 0.01, I get 0.05. That's easy enough, isn't it? Okay. Now, I ask, what's the probability of event A2 conditioned on event A1? That is, if I know that someone submitted a claim last year, what's the probability that they'll submit a claim in the upcoming year? And of course, the answer to that is it's the probability of A2 intersect A1 divided by the probability of A1. But what's a simpler name for the probability of A2 intersect A1? A2, because if someone submits a claim in the second year, of course they submitted a claim in the first year. So that's the probability of A2 over the probability of A1, which is 0.25. Now, isn't that weird? If I pick someone at random, the probability that they'll submit a claim in the upcoming year is 0.2. If I consider only men or consider only women, the conditional probability of a claim in the second year is unchanged. But if I use the whole population, it's 0.25 instead of 0.2. And I say to my boss, we should institute a safe driver program. We should try to encourage people who didn't submit claims in the previous year, because the ones who did submit claims in the previous year are worse risks for the next year, in spite of the fact that for men or for women separately, it doesn't make a bit of difference. Who can figure out what's going on?
Because if there's a claim in the first year, it's more likely to be a man.
Exactly. If someone claimed last year, that individual is more likely to be a man. You hit it right on the nose, and let's work this out. Let's work out the conditional probability of M, the person is a man, given A1. This is the probability of M intersect A1 divided by the probability of A1. What's the probability of the event M intersect A1? Pick someone at random. What's the probability that it's a man who submitted a claim last year? 0.15. And we've already worked out the probability of A1, 0.2. So you're quite right. If someone submitted a claim last year, it's 3 times more likely to be a man than a woman. And therefore, if one of your fellow agents has someone who has submitted a claim, if he just goes through the people in his file who submitted claims and picks one at random, you're more likely to get a man who is a worse risk. Now, this has interesting implications for social policy, doesn't it? Because you could argue that you shouldn't engage in gender discrimination in auto insurance, and that men and women ought to get an equal break. You shouldn't charge men more than women just because they tend to smash up their cars more. And an obvious way for insurance companies to work around this is say, we don't discriminate. We offer the same safe driver benefits to everyone, men and women equally. We don't care what your gender is. If you haven't submitted a claim, we'll give you a break on your price in order to attract you. And you can see this is gender discriminatory. In this model, you tend to get more women than men if you offer a safe driver discount. And it turns out, in fact, if you imagine any grouping of the insurable population into subgroups that have different probabilities for making a claim, then safe driver discounts are always a good deal for the insurance company and will lower the risk of a claim in the next year for the people who receive those discounts. And therefore, if you feel that insurance should be sold in a gender-neutral or anything else neutral manner, you have to go one step further and say, therefore, it should be illegal for insurance companies to offer safe driver discounts. With that thought, I leave you.